So if this were my function, the entirety of my function, I would say that the domain, which is all the x values, is, well, one way to write it would be that x is bigger than or equal to 1 and less than 7. That's a 7, by the way. The more typical standard way of writing it is using interval notation, which would be that x is an element of the interval from 1 inclusive using a bracket to 7 exclusive using a parenthesis. And this little symbol here means that x is an element of the set from 1 to 7, including 1, excluding 7. The range which is all the y values. Well, here we see the y values go from as low as 2 to as high as everything up to 8, but not including 8. So we'd say that y is between, it's greater than or equal to 2, it's less than 8. Or we could also say y is an element of the set from 2 inclusive with a bracket to 8 exclusive. I think I need to close this because it's making noise. So, and we'll talk a little bit more about domain in a minute here. Oh, there we go. My mouse isn't working for a second. Sorry. Yeah. So, and usually, like if I was going to write the domain for this first function, I'd probably just write this interval without actually saying x is an element of, but I do know some teachers do like to write this notation. So I want you to see this and be like, oh yeah, that's what that means. It just means x is in the set for everything between 1 and 7, including x. So, for some reason, my view just changed.
Is this supposed to look like an E or an arrow?
It's more like an E.
Okay.
Yeah, it kind of looks like a backwards E. That's interesting. I think not, and so I think, sorry, my video got unpinned for some reason. Oh, weird. I don't know. Anyway, we're gonna figure it all out. I think it's because someone said something, which is fine. You should say something if you have questions. I'll have to figure out how to make sure I stay pinned. But please, yeah. So yeah, it's it's kind of a backwards E. Anyway. So let's see here. I'm sorry. First day, I know I've done this, like I've taught before online, but it feels like the first day all over again, getting kind of used to how things work again. All right, so continuing on. We'll get to more domain in a minute, but let's talk, before we get to more domain, let's talk about odd and even functions. This pen is not my favorite today. Sure, I got lots of blue pens. So f of x equal to x squared is an even function. And there's a couple ways to know a function is even. The kind of the most specific way is we know it's even because f of negative x is equal to f of x. That's the definition of being even. That if you plug in a negative number, you get those same results if you plug in the corresponding positive number. For example, right, f of negative 2 is equal to negative 2 squared, which is 4, and that's definitely equal to 2 squared, which is f of 2. Right, whether we plug in a negative number or the corresponding positive number, you still get the same result. The way you would show it's the way you'd show it's even is by actually saying, well, f of negative x is negative x quantity squared, which is x squared, which is f of x. And kind of the graphical hallmark of an even function is that you have symmetry about the y-axis. So if I draw the function f of x equal to x squared, it looks like this. And this is definitely a function that is symmetrical about the y-axis, because if you flip it around the y-axis, it still looks the same. And every even function has that property. Then f of x equal to x cubed is an odd function. And the reason, or the way we justify something as an odd function, is because f of negative x is equal to negative f of x. So here, for example, f of negative 2 is negative 2 cubed, which is negative 8, which definitely is equal to negative 2 cubed, which is negative f of 2. And we could show very generally that f of negative x, if I plug in negative x for x, I get negative x quantity cubed, and the negative to an odd power is going to retain the negative. Oh, Jess, you're also welcome to ask me to go back. I don't remember what it was I erased though. Was the domain part?
Yes, I believe it was that.
So I will post the video later as well.
Oh, cool. Good. Thank you. Sorry, I forgot.
No, it's all right. But definitely feel free to like ask me to go back to something if you have questions. So negative x cubed is negative x times negative x times negative x, which is negative x cubed, which is negative f of x. So that's an example of an odd function. And graphically, x cubed is the one that I'm never really good at drawing. Looks like this. Kind of like that. Odd functions have what we call symmetry about the origin, or rotational symmetry. If you rotate this 180 degrees around the origin, it'll look the same as it did originally. So those are examples of even and odd functions. Here are a couple more examples. I can be smart and erase while I leave the other side up.
Is x cubed an odd function because the 3 is an odd number?
Well, so I wouldn't say because the 3 is an odd number, but there is definitely a correspondence for polynomials where if the powers are all odd, the function is odd, or if the powers are all even, the function's even. But it gets a little bit murkier when we have more complicated functions.
Okay.
So for example, just to kind of to go along with that, if my function was something like x times the square root of x squared minus 9, then it's not exactly clear if it's odd or even based on the powers. It is odd. And the way you can show it's odd is by showing that f of negative x is equal to negative x times the square root of negative x squared minus 9. Negative x is just negative x. But negative x squared becomes positive x squared. And we can see that this result is exactly this, except the negative of this. So this is negative f of x. And I feel like, yeah, that's what I wanted. So I see that f of negative x equals negative f of x. Now, this function, I'm not so great at graphing. But you know what is great at graphing? Desmos. Oh, there's people in the waiting room. Sorry if you were waiting in the waiting room for very long. It's certainly not my intention. But I want to show you while it's on my mind. So let me So let's do that. So I'm going to share my screen. Here is Desmos. And I'm going to graph this thing just so I can see actually the rotational symmetry. So if I graph y equal to x, let's see, square root is sqrt of x squared minus 9. You can kind of see, and if we zoom out, it might be a little bit easier, right? If we rotated this thing 180 degrees, it would look the same. Or you could also think about doing a reflection in both the x and y axis, and it would still look the same. So we can see, oh yeah, that definitely has the rotational symmetry that we're thinking of. Just like y equals x cubed also has that rotational symmetry. Just like y equal to sine of x also has that rotational symmetry, right? If you rotated that 180 degrees, it would still look the same. I wish there was a way to like do that graphically, but if there is, I don't know how to do that. On the other hand, y equals x squared is definitely even. Oh boy, that's not what I want to do. Gotta click the things. Y equals x squared is even, right? We've got symmetry about the y-axis. Y equal to cosine of x, also even, because again, if you reflect it around the y-axis, it's going to look the same. I feel like I had one more example I really wanted to do. Or any kind of conglomeration of even powers of x, meaning if you had like 2x to the 4th minus 3x squared plus 5, that also has the symmetry about the y-axis. So when you have a polynomial where all the powers are even or all the powers are odd, you have respectively an even or an odd function. But other more complicated functions don't follow that rule. So just something to be aware of. So there's some kind of nice examples of even functions. Let me make sure, let me see, I want to see one thing here.
So an even function reflects across the y-axis while an odd function reflects across the x-axis?
I wouldn't, so the first thing, yes. The second thing, not quite. So in fact, so let's go back. Let me share. I would draw things, but I'm never going to be able to draw it as well as Desmos can. And you can actually see what you want to see with Desmos. Sorry, one sec here. I lost what I wanted.
Is it that the odd function like reflects over the x-axis and the y-axis? Like
Right.
it has to reflect over both, and then
yeah. And the one thing I would say about both is that it's not just that it reflects, because you can really reflect any function across an axis. Like for example, if I take, y equal to, I don't know, what's something, the square root of x, it's neither even nor odd, but I can definitely still reflect it across either axis. I can reflect it across the y-axis by changing x to negative x. And I can also reflect it across the x-axis by putting a negative out in front of the function. right? So those are all reflections. The difference, or the kind of the important point that makes something even or odd, is that for an even function, when you reflect it across the y-axis, it looks the same, right? So y equals x squared is even because when I reflect it across the y-axis, sorry. It still looks exactly the same as it did before. So that's what makes a function even, is that when you look at it, if you were to reflect it or flip it across the y-axis, it looks the same. The problem is it doesn't work. It's not the same way for odd across the x-axis, because that would make it not a function, right? If you had a reflection that looked the same, in fact, let me stop sharing because I feel like I'm better able to explain this action. So if I had something, right, like x equal to y squared that looked like this, and I reflect, this is symmetric about the x-axis, but it's not an odd function. It's a function that is symmetric about the x-axis. Well, I should say it's an equation that's symmetric about the x-axis, because it's not actually a function, right? It fails the vertical line test. So odd functions have different symmetry. They have what I call rotational symmetry, or what other people call symmetry about the origin, where you can either, and there's actually two equally valid ways of saying it. You can either reflect it in both axes and it should look the same, or you can rotate it 180 degrees around the origin and it should look the same. Both of those are this, they really are literally the same thing. They're just different ways of saying the same thing. Okay. So one thing that is mildly terrible about teaching this stuff from home is that I don't have my notes on paper in front of me, and I have to look at my computer to look at my notes to see where I want to go next, which is fine, but I just wish it was not the case. So something that is worth knowing about these odd and even functions, specifically, is that, and I know I already said these, but I want to kind of emphasize these ones. Sine of x is odd. Cosine of x is even. And tangent of x is odd. And so what this means for us is essentially some identities. If sine of x is odd, that means sine of negative x is equal to negative sine of x. Cosine x being even means cosine of negative x is equal to cosine of x. And in fact, we can then use those two pieces of information to show that tangent is odd. We can say that tangent of negative x, well, we know that tangent is sine over cosine. So tangent of negative x is really sine of negative x over cosine of negative x. But then sine being odd means that sine of negative x is negative sine of x. And cosine being even means that cosine of negative x is just cosine of x. And then sine over cosine is tangent of x. So I've got negative tangent of x. So the tangent of negative x is equal to negative tangent of x, which means tangent is an odd function. Or I guess I should say, which shows tangent is an odd function. And we don't really do a whole lot with that information yet. Once we come back around to like chapter 4, I think, of the textbook, we'll start talking really about graphing things in earnest. And it's often nice to recognize a function is even or odd, because it kind of makes it, you only have to graph like half of it, and then the other half is just the right kind of reflection. So not super important in general to know if a function is even or odd, but there are a couple times when it's kind of useful, like when we're graphing it, or when we take Calc 2, if a function's odd, a lot of times it means the integral is going to end up being 0, which is kind of nice to know. So there are some times when it's useful to know about a function being even or odd. So let's continue on. Let's talk more about domain. So let's look at, say, find the domain and range of some of the following things. Let's start with, say, f of x equal to 9 minus x squared. Excuse me. I want to see all the things. I need a bigger monitor. I mean, not really. My monitor is large-ish, but it can always be bigger. So for this, so I should say a few things here. When I'm thinking about domain, there's really kind of three things, maybe a fourth one sometimes, but there's really three things I'm kind of looking for when I think about domain. Is there any potential division by 0? Is there any potential square roots of negative numbers? Or are there any logarithms of non-positive numbers? This function does not have any of those things. There's no division, there's no square roots or even roots, there's no logarithms. If I don't have any of those three things,
Could you write those three things down really quick?
I'm definitely gonna write them down in just a sec, yes. Yeah, if I don't have any of those three things, there are no domain issues. So this one has no domain issues. So the domain is, you can either write the set from negative infinity to infinity. Infinities always get parentheses because they're not real numbers. Or specifically when your domain is everything, when it's all the real numbers, some people like to write this fancy R with 2 vertical lines. Either way. My favorite pens are dying. It's always sad when my pens die. We'll get after this, I'll write down the things. The other thing I want to mention is that the range here. So range can be a tricky topic. Sometimes we find the range by finding the inverse function and finding the domain of that function. In this case, that's not really what we want to do. Here, we just want to graph it. So this is a parabola, 9 minus x squared. It opens, or if you prefer, negative x squared plus 9. It's just the usual parabola x squared flipped over and then shifted up by 9. It looks like this. Where the y-intercept, which also happens to be the vertex for this particular parabola, is the point 0.09. So the range, well, the y values go as low as negative infinity, right? There's no stopping how low you can go. And then go up to a y value that maxes out at a value of 9. So in this particular problem, that's how you find the range, is by just graphing and saying, okay, what's the bottom y value? What's the top y value? And often a lot, that's how we actually find the range for a function, is graphically. Okay. So let's go ahead and talk more about specifically the kinds of things to look for when you're finding domain of a function. So domain guidelines. And what I will say is there are typically 3 types of things to look for. There are a couple extra weird functions that we'll talk about when we get to them. But mostly it's these three things. So thing one, division by 0. We don't want division by 0, right? That's a no-no. Sounds, I can't believe I just said that. It sounds terrible. So what I usually think of is if our function is equal to some kind of fractional looking thing or rational looking thing, and you've got some stuff on the bottom, I don't really care what's on top, then what I want to say is that the stuff cannot equal 0. That's where I'm going to start. So actually I'm going to leave this here and we'll do some examples on the other side. So for example, if my function was say, I don't know, 5 over x squared minus 4. And I want to know what's the domain. Well, I would say, usually we set it equal to 0 and then say we're going to exclude it. So you can either say, well, I know that x squared minus 4 can't equal 0. Or what I actually probably typically write is I want to exclude the points where x squared minus 4 is equal to 0. There's a couple ways you can solve this. You can bring the 4 over and square root both sides, or I usually prefer to factor. So you can say, I'm going to factor this as x minus 2 times x plus 2 equal to 0. And then say I get x equal to 2 and x equal to negative 2. So those are the numbers I'm going to exclude from the domain. So I don't want those. So my domain is everything except for 2 and negative 2. I find it helpful to draw the number line if I'm not exactly sure how to write it. So here's what I've got. Here's my number line. I'm only going to put these points on it. And I don't want them. But I do want everything else. I want all of this from negative infinity to negative 2. Excluding negative 2. I want all of this from negative 2 to 2. So I do a union, negative 2 to 2. And I want all of this. That's everything except for 2 and negative 2. Yeah. I do want to point out, because this is something that comes up. If I were to have solved this kind of the other way, right? If I had said, instead had said, you know, x squared equals 4. And then I say, so this is where I want to say something, right? I'm going to do the square root of both sides. All right, so I have some questions that have some maybe answers that are a little bit trickier than they might seem. What's the square root of 4? Yeah, exactly, 2. And yeah, so we've got equal to 2. Now here's the trickier question, which has an answer that you might not suspect. What's the square root of x squared? And I will tell you.
Negative.
You're very close. You're on the right track with, I think you said positive or negative x.
Oh.
Yeah, but it's kind of that, except it's slightly different. It's actually the absolute value of x. Because what you want, you're right to say positive or negative x. Because if x is positive, then we want it to be positive x. But if x is negative, then we want to take the negative of that to turn it into a positive. So what you're getting here is that this ends up meaning that x can equal either 2 or negative 2. Because the absolute value of 2 is 2, and the absolute value of negative 2 is still 2. Now, it's a lot of work to kind of get to the point where you just say, well, x is plus or minus the square root of 4, which is plus or minus 2. But this is kind of the reason behind it. When you square root a square, you actually get the absolute value. I want to say 2 more words about that, just to kind of really help you believe that what I'm saying is true. What's the square root of 5 squared? I know it seems like a dumb question. Humor me. It's 5. Okay. What's the square root of negative 5 squared? That seems like it's hard to see. Let me write that again. What's the square root of negative 5 squared? It's also 5. Because negative 5 squared is still 25, and the square root of 25 is still 5. So this is what I actually mean when I say that when you take the square root of x squared, you get an absolute value of x, because it's doing exactly what the absolute value does. This is the same as the absolute value of 5. This is the same as the absolute value of negative 5. It's inputting a number and giving you back the same number if it was already positive, or the opposite number if it happened to start off being negative. So anyway, just want to mention that. Back to domain. So division by 0, you don't want the bottom to be 0. The second thing we look for is even roots of negatives. So we can't take the square root of a negative number and get a real result. Yes, there are imaginary or complex numbers. That's totally something that we don't really talk about in calculus, but it's definitely something that's out there. But if you're talking about the domain of a real valued function, which is all the functions we're going to talk about, then we don't want square roots or even roots of negatives. So it could be a 4th root, a 6th root, a 1000th root. So if my function f of x is the square root of some stuff, wow, this pen is going. Then what I'm going to say is that I want the stuff to be greater than or equal to 0. Right? I don't want to take the square root of a negative. So I want the argument or the insides of the square root to be positive, non-negative. And I should go a little bit further. I should really say it could actually be, right, any root as long as the root is even. So it could be a 4th root or a 6th root or et cetera, et cetera, et cetera. A couple examples of this. Only 2 examples. So g of x equal to the square root of 4 minus 6x. So if this was my function and I wanted to find the domain, I would find the domain by setting the insides, so 4 minus 6x, to be non-negative, greater than or equal to 0. And then in this case, since it's a linear equation, right, I only have x to the first power and no other powers of x, I can just isolate x. So I can add 6x to both sides. So 4 is bigger than or equal to 6x. And I can divide both sides by 6. So that 4/6 is bigger than or equal to x. Or reduce that fraction, 2/3 is bigger than or equal to x. Typically, we're going to want to write our domain in the interval notation. So we have to be a little bit careful, right? Is x bigger than 2/3 or less than 2/3 here? I've kind of written it in a backwards way, but it's definitely less than 2/3. So you could, if you wanted to, you could rewrite this as x less than, I should say less than or equal to. less than or equal to 2/3. So you can draw the number line if you want. There's 2/3. I want everything to the left, including that point there. So my domain is negative infinity to 2/3 with a bracket. One thing I've kind of noticed about domain problems is that when you've got a problem where you've got a fraction kind of thing, like this kind of thing here, usually you just end up excluding a couple points here and there. Whereas when you've got a domain question with a square root or an even root, you end up kind of excluding a whole section of the real number line. That's one main difference I have noticed over the years. These types of problems can get a little more complicated, but actually let's talk about the last kind of domain thing, and then we will come back to this. So the other thing we don't want is logs or logarithms of non-positive numbers. So we can't take the logarithm of 0, we can't take the logarithm of a negative number. So if f of x is equal to some log, with, it doesn't really matter what the base is, I'll just say log base b of some stuff, then what we want to have to say is that the stuff has to be strictly greater than 0. We don't want the stuff to equal 0. We don't want the stuff to be negative. So here. So for example, I could say, what's the domain of g of x equal to the log base 2 of x to the 4th minus 5x cubed minus 6x squared. And if we saw a question like this, our first step would be to say, okay, well, I know that the inside part, x to the 4th minus 5x cubed minus 6x squared, has got to be greater than 0. And then we would have to do this one by doing some factoring. So the previous one we did, we were able to solve the inequality by just saying we can solve for x. Here we can't really do that. We have to figure out where the left-hand side is equal to 0, and then kind of look at the number line. So I'm going to factor. I see I can factor out x squared. I'm left with x squared minus 5x minus 6. And then I want to factor this further if I can. This one is always tricky with the 5 and the 6, because you need things that multiply to -6 and add up to -5. That would be -6 and +1, not 2 and 3, right? It's always tricky with 6 and 5. It can be 2 and 3, it can be 6 and 1. It's always only one of them. Things only ever factor one way. It's the fundamental theorem of algebra. You can only factor things one way. If it was a +6 here, then it would be -2 and -3. It's not. It's a -6, so it's -6 and and +1. So now we've factored it completely, x squared times x minus 6 times x plus 1. And now we're going to see where on the number line this expression is positive. And to do that, I'm going to plot all the zeros. So what makes this equal to 0? Well, 0 for sure, +6, and -1. You need to write them in the right order. So that's where they go. And then we're going to test a point. So the thing I'm trying to say here, I'm not doing a great job of saying, is each of these individual sections are all going to be the same sign. Meaning, once I know the sign for one number that's bigger than 6, everything that's bigger than 6 will have the same sign. Because the only way you can change signs is by going through 0. And this thing is only equal to 0 at those 3 spots. So I'm going to pick a number larger than 6, like 7 or a billion or whatever number larger than 6 you want to pick. If I plug it in, 7 squared is positive, 7 minus 6 is positive, 7 plus 1 is positive, and a positive times a positive times a positive is positive. I don't care what the value is. I just care whether it's positive or negative. And then you have a choice. You can either keep doing the same thing. You can say, okay, I'm going to pick a number between 0 and 6, like 3. And 3 squared is positive, and 3 minus 6 is negative, and 3 plus 1 is positive. So it's positive times a negative times a positive, which is negative. Or you can use the method where you look at the multiplicity of the factor that the 0 came from. So this 0, x equal to 6, it's called a 0 because it makes the expression equal to 0. This 0 came from this factor. This factor has an odd multiplicity. When the multiplicity is odd, the sign changes. When the multiplicity is even, the sign stays the same. So from here to here, 0 came from this factor. This factor has an even multiplicity, so the sign is going to stay the same. You can also check, right? Let's pick a number like 0, between 0 and negative 1. I guess we'll pick negative 1/2. Negative 1/2 squared is positive. Negative 1/2 minus 6 is definitely negative. And negative 1/2 plus 1 is definitely positive. So it's a positive times a negative times a positive, which is still negative. The reason that the sign doesn't change is because the part that would change is this part here. But since it's being squared, it doesn't matter if the insides are positive or negative. Overall, it's not going to change signs because this thing being squared is always going to be positive. So that's why the even multiplicity terms don't actually, that's why the even multiplicity terms, the sign doesn't change when you go from one side of them to the other. On the other hand, negative 1 came from this x plus 1 factor with an odd multiplicity. It's definitely going to change signs. This is the same kind of reasoning that we use when we graph polynomials to say whether the graph bounces or crosses, right? You bounce when the sign stays the same. We bounce at an even multiplicity. We cross when the sign changes, or we cross when we have an odd multiplicity. So if I was actually, no, I don't want to say that actually. So back to the question, we want to know when this is greater than 0. Well, it's greater than 0 when it's positive. So it's greater than 0 in this interval and in this interval. So my domain here would be everything from negative infinity to negative 1, exclusive, union, 6 to infinity, exclusive. So, yeah, we're going to come back to this in just one second. I want to say something that's kind of interesting. Just to kind of recap, these are your general domain guidelines. We don't want division by 0. So if you have a fraction, you want to make sure the denominator isn't 0. We don't want to take square roots or even roots of negatives. So if you've got a square root or an even root, you want to say that the stuff has to be bigger than or equal to 0. And we don't want to take logarithms of negatives or 0. So if you've got a logarithm of something, you have to say that that stuff is greater than 0. I did want to point out something that occasionally comes up, which can be a tiny bit tricky. I'm gonna do a teacher cheater thing here where I make a new problem, which is almost the same as the old problem, by changing this to f of x equal to the 6th root of that. I know. I hate it when teachers do that too, but I've only got limited space. So the only difference between this problem as far as a domain question and the previous problem is that instead of saying that the stuff has to be greater than 0, we're now going to say that it has to be greater than or equal to 0. Which means that we're still going to essentially get the same domain, except what other points do we now have to include? Well, I have to include all the values that make it 0. So I have to include -1 and 6 and 0, which is kind of the tricky one, right? I definitely have seen a lot of students say that the answer to this question is -∞ to -1 bracket union 6 to infinity with a bracket on the 6. And the problem there is that they're actually missing one important point, the 0. How do you write the 0? Well, the way you're supposed to write just one point all on its own is like this. You want to write the 0 in between braces, are what those are called. It's the set containing just 0 and nothing else. And it's kind of funky. Some people write this like 0 bracket 0. It's not really right to do that, although I've definitely been fine with that in the past. So that's the only difference between this one and the other one, is that you have to include all the points instead of excluding them. Oh yeah.
About the second guideline where n has to be even. So if it's odd, what happens?
If it's odd, there's no restriction. It's an excellent question. So yeah, you asked a good question. So if our function was, say, the 5th root of, doesn't really matter, x squared plus 7x plus 6, and I asked what's the domain, I would say, well, I don't have any of the 3 restrictions. I don't have an even root, I don't have a fraction, I don't have a logarithm. So the domain here is all real numbers. Which I've written terribly. And the reason for that is because we can always take an odd root of a negative number. For example, well, this isn't the example we're getting to, but what's the cube root of 8? You can show them on your fingers. Yeah, exactly. The only thing I don't like about my video being pinned is I can only see like 5 of you, which is a bummer, but it's the way it goes. So I should try and cycle through so I can see other people too. Yes, the cube root of 8 is 2 because 2 times 2 times 2 is 8. All right, well, what's the cube root of -8? Well, it's -2 because -2 times -2 times -2 is -8. So you can always take an odd root of a negative number. Sometimes it's just not very interesting. Like we can also take the cube root of 5. It's just the cube root of 5. There's no better way to say the cube root of 5, right? There is some irrational number, 1 point something, that if you multiply it by itself 3 times, you get 5. I don't know what it is exactly. I mean, no one knows what it is exactly. It's the cube root of 5. That's the best way to say it. But you could look at it on a calculator and you could say, okay, oops, that's not what I want to do. The cube root of 5 is approximately 1.7, but I mean, it's the cube root of 5. And then the cube root of -5 is also some real number, but I mean, it's approximately -1.7. So even roots, you can't take an even root of a negative number, but you can always take an odd root of a negative number. And more interesting, maybe not more interestingly, the odd root of the negative is just going to be the negative of the odd root of the positive. Or in a better way, odd roots are odd functions. F of x equal to the cube root of x, or g of x equal to the fifth root of x, for example, are both odd functions. Right? If you take the cube root of a positive number, you get a positive result. If you take the cube root of a corresponding negative number, you get the corresponding negative result. And you can also see this graphically. And again, as much as I would like to pretend like I'm a great person when it comes to graphing, I'm not. So I will share instead. Why am I so bad at sharing my screen? It shouldn't be that hard. Sure. There we go. So if we look at, say, let's delete these. So, I don't actually know how to do a cube root. Well, that's not true. I don't know how to write it like I want to write it. Let's see. I get a 3 out there. That doesn't look right. So here's how I would do it. So a cube root is the same as a 1/3 power. So I would write it as x to the 1/3. Right? That'll do. I don't actually know the way to write it so it looks different. I'm sure there's a way.
If you try clicking, the up in the bottom left, it might help.
Yeah. I see a square root, but I don't see like a, I mean, you know what? You don't need it. You can always write a root as a power. So fifth root is a 1/5 power. That's how I'm going to write it. So both those functions, we can look at them and see, oh yeah, those definitely have the odd symmetry. If we rotated those 180 degrees, they would look exactly the same as they did when we started with them. So yeah, that's all I wanted to show you. Now I'm going to have to figure out how to write a cube root the other way though, because yeah. So let's see here. Domain can get a little more complicated when we start kind of throwing things together. For example, if my function was something like, I don't know, x plus 2 over 3 minus the square root of x. Now I've got kind of a couple different domain issues that could come up. And so I have to think about all the possible things that are problems. So thing one, I don't want the denominator equal 0. So I want to exclude 3 minus the square root of x equal to 0. I can definitely solve that equation. 3 equal to the square root of x, square both sides, you get 9 equal to x. So we definitely don't want 9, right? 9's a problem. And then we also need, for our square root, right, we have a square root of x. So we have to say, well, the insides of the square root have to be greater than or equal to 0. This one, there's nothing else to do, right? We've already solved the inequality by just writing that down. So then we need both of these in conjunction with each other. So looking at my number line, there's 0, there's 9. I want x to be greater than or equal to 0. So I want all of this and all of this, but I don't want this. And I don't want any of that over there. So here my domain would be 0 inclusive, right? 0 is fine. Square root of 0 is 0. It's a perfectly good number to take the square root of. Up to 9 exclusive. And then everything from 9 to infinity.